Welcome everyone, I'm Norman Wahlberger, and today it's arithmetic with money. We've talked about how weighing things, measuring things, looking at the volumes of things connects with arithmetic. Money is another really important connection with the real world. And in some ways, it's actually perhaps the most powerful one because the Hindu-Arabic number system aligns itself very well with at least most money or currency systems in use today based on a base 10 system. And we'll see that this really strong correspondence actually gives us some hints. And we'll have a surprising twist at the end of this video as we start to move towards understanding really novel ways of doing important arithmetical tasks. Okay, so connecting arithmetic with money is powerful, but we'll also see that there's a disconcerting aspect to it, and that overcoming that disconcerting aspect really introduces some surprises. So we're going to assume that we're working in a currency system like, say, the dollar, where our main unit is, say, $1, and that we also have a $10 bill and a $100 bill and a $1,000 bill. Okay, and we'll ignore any other units that might be floating around. So it doesn't have to be dollars, it could be euros or yen or whatever you like, as long as we think in terms of a $1, $10, $100 and $1,000 as being sort of fundamental units, and we have bills or perhaps coins that represent these. Now, there's a natural correspondence between the $1 and our representation of one as a single row rectangle, just one square. And I remind you that when we had 10, we had a shortcut for that involving a red square. So the $10 and the red square are sort of compatible, and that corresponds to the number 10. We'll put a little red strip to the right of the $10 bill so we can easily recognize it. The $100 bill will have a green aspect, corresponds to a green square representing 100, and our $1,000 bill will have a black aspect corresponding to a black square corresponding to 1,000. Now in Australia, there is no $1,000 bill, and these days there's also in the US no $1,000 bill, although there used to be. So in practice, we'll probably mostly be thinking about $1, $10, and $100, but theoretically you could have bigger bills, and that connects a little bit more easily with our arithmetic because now we can smoothly talk about ones, tens, hundreds, and thousands in our Hindu-Arabic number system as corresponding with actual physical bills. So let me remind you of our conventions with colors here, just to be very concrete and specific. We're assuming that a red square represents 10 blue squares, which are sort of empty. And a green square represents our strip of 10 red squares. So this is 10, well the green one represents 100, and a black one represents a strip of 10 green squares, which is then 1,000. Okay, so we can use these rectangles of different colors to then concisely represent numbers as row rectangles, but perhaps sort of stacked on top of each other to make it easier to read what's going on. So for example, here is a certain amount of money. We have a dollar bill, three dollar bills. We have two $10 bills, a single $100 bill, and two $1,000 bills. That's in our wallet today. And over here is a representation of that using this row rectangle framework. Okay, the $300 bills are represented by these three squares, the two $10 bills by these two red squares, the $100 bill by this green square, and the $2,000 bills by these two black squares. This is very concise, so we don't have to string out thousands of squares in a huge row rectangle. This is much more effective, and it's really the same principle that underlies our Hindu-Arabic number system, where we record the number of ones, the number of tens, the number of hundreds, and the number of thousands. And you see there's an exact correspondence here. This 3 here, that's the number of ones, or $1 bills. There's 2 here, number of $10 bills, there's representing that 2. The 1 here corresponds to this 1, and the 2000s in black correspond to this digit here. So we have money over here, rectangles over here, and numbers over here, and there's a natural kind of parallel. We can go from one to the other very smoothly. So this correspondence between money, diagrams involving rectangles, and numbers, it's very attractive. Okay, it allows us to go from one to the other. Because, for example, addition of money is naturally then related to the addition of numbers. Okay, so the arithmetic here and the arithmetic here are parallel. But, and it's a very important but, there's a qualification that needs to be made. And that's represented in this diagram by the fact that this is a solid correspondence, while this one here is dotted. There's something a little bit nebulous about this correspondence. So there is a hitch to this story, and this hitch has a major impact for arithmetic. And it's closely connected to a fundamental problem which actually pervades a lot of primary school arithmetic, which I call the problem of carrying. The problem of carrying. Okay? That's closely connected to this slight ambiguity or hitch that's involved here. And understanding this story will be critical to be able to move forward into a new light, into a new understanding, a better appreciation of how to really do arithmetic effectively. So to try to appreciate this, let's ask the following simple question. How do we actually add money? If I have a bunch of money in this hand, and I have a bunch of money in this hand, how do I actually go about adding those two sums of money? Well, the answer is surprisingly simple. We just put the money together. Okay? We take the money over here and the money over here, and we combine them in a separate pot. We just put them together physically. Okay? We put them together physically. We just dump them together. That's how we add money X and money Y. Note, no arithmetic in the usual sense is really needed here. Okay, we don't need to be experts in arithmetic to combine this amount of money with this amount of money. We just go bang. There you go, we've added the money. Okay, that's interesting. It's subtly but importantly different from doing ordinary arithmetic. If we ask the same question about how we add numbers represented as row rectangles with our color system, then we get an answer which is very parallel to that for money. So adding row rectangles representing, say, money, it also has a natural, direct, and physical definition. We just combine the respective rows physically. So for example, here is a rectangle diagram which might represent a certain amount of money. And here's another rectangle diagram representing perhaps another sum of money. And we want to add these two row rectangles and in a way that's corresponding with addition of the monies. So what do we actually get? Well, here there are 1, 2, 3 ones, and here there are 4 ones. When we combine them, we're going to get 7 ones. 1, 2, 3, 4, 5, 6, 7. But in fact, we don't actually need to have that understanding of the names for the words. We could just actually take this rectangle physically and move it over here, and we can take this rectangle physically and abut it to the one we've just had. Okay? We just put them together physically, perhaps without even knowing how many squares each of them has. It's just a physical process. Same thing with the red squares. We just put these red squares and these red squares together to form that larger rectangle of red squares. Same for the green ones and same for the black ones. So this operation can be performed without actually any knowledge of Hindu Arabic numbers. If you went back to some former culture or time before the Hindu-Arabic tradition, they would still completely understand what you mean by saying that this rectangle system or diagram and this one here combine to give you this one. And it's exactly parallel, if you think about it, to the way we added numbers. The dollar bills in both piles combine to give you a bigger heap of dollar bills. The $10 bills combine to give you a bigger heap of $10 bills. The $100 bills combine to give you a bigger heap of $100 bills. And the $1,000 bills, if you have any, combine to give you a larger heap of $1,000 bills. But, of course, from our Hindu-Arabic point of view, we can also interpret this. We can say, but wait a minute, this is actually representing a certain number. 3 ones, 2 tens, a single hundred, and 2,000. So this is 2,123. And over here we have 1,634. And when we add them, we get 3,757. So yes, we can interpret what's going on here in terms of Hindu-Arabic numbers, and it does correspond with the arithmetic in that framework, but it's not necessary to do that. There's something elemental, physical, direct about this way of combining rectangles, just as there was for the combination of monies directly. All right, and now we get to the hitch in this correspondence. Because when the quantities involved are a little bit bigger, then we get an obvious difference between this kind of arithmetic with rectangles and the Hindu-Arabic equivalents. And we can illustrate that with this example. So here, the diagrams are just a little bit bigger, and this will show us the issue. Okay, so here's another rectangle kind of number. A certain number of ones, tens, hundreds, and thousands. And here's a second one, ones, tens, hundreds, thousands. Let's see what happens when we combine them. So again, we just work physically. We just take this rectangle here and we put it there. We take this little rectangle of ones and put it there and abut them. Okay, and we get this larger one. Now, from our point of view, we could count just to make sure we've done it correctly. 1, 2, 3, 4, 5, 6, 7 there. And 2 there, 7 plus 2 is 9, and 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, we've done that correctly. What about over here? There's that 3 there, and then this segment here is the same as this segment here. We could check that because this is 3, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 plus 9 is 12, and this one is also 12 because it's 3 more than the 9. And over here, this green one and this green one give us this one, and this black one and this black one together give us this longer black strip. So this is how the addition goes at the level of these colored rectangles, which is sort of geometrical equivalent to what would happen if we actually did it with money, with dollar bills, $10 bills, $100 bills, and $1,000 bills. But also, we could interpret what's going on here in the Hindu-Arabic system. This is 2,837. This is 5,292. And what happens when we do this addition in the Hindu-Arabic system? Well, that's a little bit more complicated. We actually haven't too much experience with such bigger numbers, but you as educators will know how to do that. You can check that you get 8,129. And how does that compare with what's over here? Let's have a look. The 9 in the ones column. Yes, there's 9 in the ones column. The 2 over here in the tens. There's not 2 over here in the tens. The 1 in the hundreds. There's not 1 in the hundreds. The 8 over here. 1, 2, 3, 4, 5, 6. There's not 8 in the thousands either. This answer does not correspond with what you get when you do the addition in the Hindu-Arabic numeral system. It's different from the previous example. In the previous example, we had exact correspondence. And why? Well, you know why. Because the numbers that we're getting here, these row rectangles, are bigger than 9 in some cases. And in the Hindu-Arabic system, we're limited to having at most 9 in any one of these digits. So we have to sort of cut up these things and replace them with a square of a larger color. But we haven't done that at this stage here. Okay? So this is really a sort of physical aspect or physical analog of the carrying problem in ordinary arithmetic. That's exactly what we're facing here. So in the Hindu-Arabic numerical system, that's a great system, that's very powerful, etc. We are allowed to use at most 9 of any unit. We have a certain number of ones, tens, hundreds, thousands, and then perhaps further higher units. But the numbers appearing here are always at most 9. They can be 0, 1, 2, up to 9. So here we have 9 ones and 7 tens and 100 and 3 thousands. That's the system, and that's a very powerful aspect of the Hindu-Arabic number system, but it does mean that there's a gap between the correspondence of these kind of Hindu-Arabic numbers and the amount of money in our wallets. Why? For the simple reason that our wallets are not constrained by this restriction. We are allowed to have more than 9 $1 bills in our wallet. There is no law against it. You can carry out 20 or 30 or 100 $1 bills in your back pocket. So for example, if you want to go and buy a new color TV, that might be thousands of dollars. In Australia or the US, you're going to have to pay for that if you're using cash, okay, with money that's probably mostly $100 bills. And you're going to need more than 9 $100 bills to do that. There's no $1,000 bills that you can use instead of 10 $100 bills. So actually, there is kind of a disconnect between our money system and this Hindu-Arabic story. And so understanding that, and maybe even taking advantage of that, will be a big step forward for us in understanding basic arithmetic. All right, so with this slide here, I'm going to open up arithmetic in a new direction. So let's have another look at money. Okay, when we're looking at money, there's no such restriction that we have to have at most 9 of anything as we have in the Hindu-Arabic system. So for example, you could have some money in your pocket that is basically this. These are $1 bills, okay? And you're not going to be able to count them that easily, but I'll count them for you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 $1 bills in a stack there. You can see there's 2 $10 bills, and over here there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 $100 bills. It's a perfectly legitimate wad of money to have in your pocket. How do we represent that? Well, we can do the same kind of thing that we do with the Hindu-Arabic numeral, but we can be more flexible. We can be more open, okay? We can represent this directly with what we see. We have 12 ones. We have 2 tens. We have 15 hundreds. We can put that information together in a little list separated with commas, because if we don't have commas, then we're going to confuse that with something else. But with the commas here, we can see that this is in the rightmost position that corresponds to ones. This is in the next position that corresponds to tens. And this is in the next position that corresponds to hundreds. So this is a new kind of number. It's still a base 10 kind of number. It still has ones and tens and hundreds. It's still a place value number, but it's more flexible. It's more open. It's a powerful new idea. Now, a very similar story happens with the row rectangle kind of diagrams. They also can be represented in a more general way. There's no intrinsic restriction on the size of the rows that appear in such a diagram. There's nothing, for example, to prevent us looking at a situation like this where we have, say, 12 ones and 11 tens and 5 hundreds and 13 thousands. That would represent also a certain amount of money. Okay. Now, if we wanted to represent this in a sort of base 10 system, we could do the following. We could still record the number of ones, the number of tens, the number of hundreds, the number of thousands, sequentially, but this time separated by commas, signifying this is not a Hindu-Arabic number. It is something else. It's something closely related, but it's something different. We're going to call them open numbers in our next video. Okay? So this is a new kind of number which will turn out to be hugely useful in teaching young children to do arithmetic well. Now, it might be disconcerting to think, well, okay, we're introducing new kinds of numbers to do arithmetic. But I remind you that in the modern world, we actually already have an alternate system of doing arithmetic, which is what our computers are based on. So our computers don't use Hindu-Arabic numbers directly. They convert things into binary, okay? Numbers which are based on a base 2 system. And that's convenient for them because having 2 possibilities is more natural if you're a machine than having, say, 10 possibilities. And they're quite good at converting a problem that we might give them in base 10 to this base 2 system, working it out in base 2, and then converting back to our base 10 system. So that's the kind of thing that we're going to be thinking about here, to augment, not replace, but augment our Hindu-Arabic framework with these new kind of open numbers. And this will be just what we need to make addition and multiplication algorithms much more logical, much more simple, and much more powerful and easily checkable. Okay, so it's going to be the stepping stone to huge technological advances in the education of young people with basic arithmetic. And I'll tell you how that goes in our next video. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.